Previously, we've analyzed the motion of a vibrating mass that oscillates about some equilibrium position. This mass happened to be a mass on a spring. A spring mass system is a good model for many real-life vibration systems. We've previously derived its displacement, its velocity, and its acceleration. The acceleration is a consequence of a force that pulls the mass back to its equilibrium position. This force is called the restoring force. This restoring force increases linearly with the displacement of the mass from its equilibrium and is dependent on the property of the mass called the spring constant. This is known as Hooke's law. So if there are no other forces acting on a spring, then the restoring force produces the net force and the net acceleration. If we rearrange this equation to solve for acceleration, we find that the acceleration of a spring is equal to the ratio of the spring constant and the mass multiplied by the displacement. Acceleration is high for high spring constants, but decreases for large masses. In the video where we derived the acceleration equation for an oscillator, we found that the acceleration is proportional to the square of the angular frequency and the displacement, and can be written as minus omega squared times x. Eliminating the negative signs and x on both sides of the equation shows that the square of the angular frequency is equal to the ratio of the spring constant to the mass. Thus, the angular frequency is equal to the square root of the spring constant divided by the mass. Since the angular frequency is equal to 2 pi times the frequency of oscillation, then the frequency must be equal to 1 over 2 pi times the square root of the spring constant divided by mass. And of course, the frequency is equal to the inverse of the period of oscillation. So the period must be equal to 2 pi times the square root of the mass divided by the spring constant. Knowing the period or frequency of the oscillation allows us to predict the motion of the vibrating mass by utilizing the acceleration, velocity, and displacement equations derived in the earlier video. Consider the following example where there are 3 springs. The springs are at rest without any masses attached. We're going to take a 50-gram mass and attach it to the first spring. We'll then slowly release the mass until it stretches the spring to its maximum length. This stretch length happens to be 5 centimeters for this spring. So relative to the ruler on the screen, the spring is now stretched to a position of 25 centimeters. The mass is hanging there without any movement. So what is the net force acting on the mass? Because the 50 kilogram mass is stationary, there is no net acceleration. Therefore, there is no net force. That is, the sum of all of the forces acting on the mass is 0. We know that gravity acts on the mass and applies a force equal to the mass times the acceleration due to gravity. This force is essentially the weight of the mass. So in effect, we've applied a force on the spring equal to the weight of the mass. This applied force causes the spring to stretch by 5 centimeters, so its displacement from its unstretched length is 0.05 meters. Using Hooke's law, determine the spring constant for this spring. If we now put the mass an additional 15 centimeters, so that the spring is stretched to 40 centimeters, then we let it go, it will start to oscillate. Assuming that the spring is an ideal spring with no friction, it will continue to oscillate indefinitely. What is the equilibrium position of the spring mass system relative to the ruler? What is the amplitude of the oscillation? In one cycle, how far does the mass travel? Now that we know the spring constant for spring 1, we can work out the angular frequency of the oscillation using the previously derived formula, omega being equal to the square root of the spring constant divided by the mass. So what is the angular frequency of this oscillation? The spring constant is 9.8 newtons per meter, and the mass is 50 grams or 0.05 kilograms. So the angular frequency is the square root of 9.8 divided by 0.05, which comes to 14 radians per second. Knowing the angular frequency now lets us work out the frequency and period of oscillation. Given that the angular frequency is equal to 2 pi times the frequency, then what is the frequency of this oscillation? So a mass oscillates at a rate of 2.2 cycles per second. This means that the period of oscillation is the inverse of 2.2 Hz, or 0.45 seconds. So it takes a mass 0.45 seconds to complete one full cycle. As we know the amplitude of the oscillation, we can now determine the displacement of the oscillating mass about its equilibrium at any time using the displacement equation. The displacement equation is the amplitude multiplied by the cosine of the angular frequency times the time. Substituting the values for amplitude and angular frequency gives us the displacement being equal to 0.15 multiplied by the cosine of 14t. We can also determine the velocity of the oscillating mass as a function of time using the velocity equation. The velocity equation is the negative of the angular frequency multiplied by the amplitude multiplied by the sine of the angular frequency times the time. So substituting the values for amplitude and angular frequency gives us the velocity equation being equal to minus 2.1 times the sine of 14t. Finally, we can determine the acceleration of the oscillating mass at any time using the acceleration equation. The acceleration equation is the negative of the angular frequency squared multiplied by the amplitude multiplied by the cosine of the angular frequency times the time. Substituting the values for the amplitude and angular frequency gives us the acceleration equation being equal to minus 29.4 times the cosine of 14t. In summary, the angular frequency of a spring mass oscillator is equal to the square root of the spring constant divided by the mass. Since the angular frequency is equal to 2 pi times the frequency, then the frequency must be equal to 1 over 2 pi times the square root of the spring constant divided by the mass. The period of oscillation is the inverse of frequency, so the period is equal to 2 pi times the square root of the mass divided by the spring constant.